So in the previous video, we implemented a perceptron in Python, and we saw that it actually works. Now in this video, let's evaluate its performance and visualize its decision boundary. Based on the previous video, we already know that the perceptron doesn't make any mistakes on the training dataset. Nonetheless, let's implement a compute accuracy function here, which computes the accuracy on that dataset. We use that function so that we can also compute the accuracy of the perceptron on other datasets, for example, the validation and the test dataset. So how it works is similar to computing the error. However, here we are counting the number of correct predictions. So we start with 0 correct predictions, and then we are iterating through the dataset and perform the forward passes. So the forward pass returns the class label, and then we are simply counting the number of times the predicted class label matches the true class label. And then once we have the number of correct predictions, we divide this number by the size of the dataset here to obtain the accuracy. So since we only have a training dataset at this point, let's apply our compute accuracy function to the training set. So we can see here the training accuracy is 1, which is kind of what we expected based on the 0 error in epoch 4 and 0 error in epoch 5. This compute accuracy function is a general purpose function though that we can also use on validation and test sets, which will be very important when we evaluate real neural networks later on. Note that the accuracy is a number between 0 and 1, and personally I prefer to write down the accuracy as a percentage. So here I can also print the percentage by multiplying this number by 100. So last but not least, let's also take a look at the decision boundary of the perceptron. So for that, let's start with the plotting code that we used above. So here, that's simply the code that we used before in part 1. So here is the data set again, and now we are trying to visualize the decision boundary of the perceptron. So if you watch the optional video for plotting this decision boundary, the way we can compute the decision boundary is by setting the weighted sum to 0 and then solving for x2. So once we have this equation, we can then provide x1 as an input and calculate x2 from it. How we obtain this, I would recommend to watch the video again if this is unclear, but also for now, maybe you don't have to worry about these details and just follow along with the code. Then we have two x1 values. We set x1 to equals minus 20 and x1 max to 20. Why do we use these particular values? Well, they are kind of arbitrary. I'm just trying to choose values that are very far off the plot so that the decision boundary covers the whole plot. So for x1 minus 20, this would be on the x1 axis somewhere here on the very left. And for the x1 max here, this would be 20, so it would be somewhere far here on the right. So I can then implement this function and be sure that the decision boundary, wherever it is, would cover this whole plot. So now let's run our plot boundary function on the perceptron model to obtain these x values here. The code that you can see here is exactly the same code like before. The only difference here is that I inserted this plotting code for the decision boundary based on these x values. So the results are shown in this plot here, and we can see, based on the decision boundary, that the perceptron classifies all the data points correctly. All the orange triangles fall on the right-hand side of the boundary, and all the blue diamonds fall on the left-hand side of the boundary. Yeah, and this is it for the hands-on coding section on the perceptron.